Far out in the depths of space, hidden in the endless black, there are mysteries that challenge everything we think we know about the universe. Imagine stars so strange, so fundamentally different, that they don't shine like the ones you see in the night sky. These are dark stars, monstrous celestial objects that defy the rules of physics as we understand them. They don't burn, they don't flicker, they exist in shadow, feeding on something far more bizarre than ordinary starlight. And yet, they might hold the key to some of the greatest unanswered questions in astrophysics. For centuries, humans have gazed up at the heavens, mapping the familiar twinkling lights we call stars. But what if we've been missing something far more extraordinary lurking in the darkness? Dark stars aren't just another cosmic oddity, they're a radical rethinking of how celestial bodies can form, powered not by nuclear fusion but by the annihilation of dark matter itself. Picture a star that burns with an invisible fire, growing to unimaginable sizes, dwarfing even the largest supergiants we've ever discovered. If they exist, these cosmic giants could reshape our understanding of the early universe, rewriting the story of how galaxies came to be. This is the frontier of modern astrophysics, a place where theory collides with the unknown, where scientists chase ghostly signatures in telescope data, hoping to catch a glimpse of something that shouldn't exist and yet might. The hunt for dark stars isn't just about filling gaps in our knowledge, it's about confronting the possibility that the universe holds secrets far stranger than we've dared to imagine. So tonight, as we peer into the void together, we're not just exploring distant objects, we're stepping into a mystery that could change everything, and the deeper we go, the more astonishing the journey becomes. Long before the first flickers of starlight pierced the cosmic darkness, the universe may have birthed something far more alien, primordial dark stars. Picture a time when space wasn't filled with galaxies, but with a seething ocean of hydrogen, helium, and something far more mysterious, dark matter. In those early moments when the cosmos was just a few 100 million years old, gravity began pulling these ingredients together. But unlike ordinary stars, which ignite through nuclear fusion, these ancient behemoths might have drawn their power from something invisible. Dark matter, the elusive substance that makes up most of the universe's mass, could have collided and annihilated within their cores, releasing enough energy to fuel stars hundreds of times larger than our Sun. Think of them as cosmic furnaces running on an entirely different fuel. While modern stars like our Sun shine by fusing hydrogen into helium, primordial dark stars would have glowed faintly with the heat of dark matter particles destroying each other. That subtle glow wouldn't just make them dim, it would let them grow to staggering sizes. Some theories suggest these stars could have ballooned to millions of times the mass of our Sun, becoming so massive that their gravity would warp space itself. And here's where things get even stranger. When these ancient giants finally collapsed, they might not have left behind the dense remnants we see today. Instead, they could have imploded directly into black holes so vast they became the seeds for the supermassive monsters lurking at the centers of galaxies. That's the real puzzle. If dark stars existed, they could explain one of astronomy's biggest mysteries: how supermassive black holes appeared so early in the universe's history. Normally, black holes form from dying stars, growing over billions of years by swallowing gas and merging with others. But some of the oldest supermassive black holes we've spotted formed when the universe was less than 1 billion years old, far too quickly for the usual process. Dark stars offer a tantalizing solution. Imagine a star so massive it bypasses the usual death throes of a supernova and simply folds in on itself, creating a black hole already primed to grow. These primordial dark stars wouldn't just be relics, they'd be the architects of the cosmic structures we see today. Yet for all their potential significance, dark stars remain ghostly figures in our theories. No telescope has definitively spotted one yet, but astronomers are searching for telltale clues in the faintest, oldest light we can detect. If they're out there, their signatures would be unlike anything else in the night sky, objects too cool and diffused to be quasars, yet too massive to be ordinary stars. Finding one would be like uncovering a fossil from the universe's infancy, a window into a time when the rules of physics played out in ways we're only beginning to imagine. Until then, they linger in the realm of possibility, shadowy titans from the dawn of time, waiting to rewrite the story of the cosmos. Gravity doesn't just pull, it bends, warps, and distorts. And when you're dealing with an object as massive as a dark star, that distortion becomes its own kind of signature. Imagine a celestial body so dense and heavy that it doesn't just trap light, it twists the very fabric of space around it, creating a funhouse mirror effect on a cosmic scale. This isn't science fiction. It's a phenomenon called gravitational lensing, and it might be the key to spotting these invisible giants hiding in the darkness of space. Here's how it works. When light from a distant galaxy passes near a massive object like a dark star, the star's gravity acts like a lens, bending the light waves around it. From our vantage point, that background galaxy might appear stretched, duplicated, or even warped into a glowing ring, a cosmic mirage revealing the presence of something unseen. Astronomers have used this trick to map dark matter clusters and distant black holes. But what if some of those lensing anomalies we've already detected aren't caused by galaxy clusters or black holes at all? What if they're the fingerprints of dark stars lurking undetected in the data? The strangest part, we might have already seen them without realizing it. Some gravitational lensing events don't quite fit the usual patterns. Take the case of a faint, unexplained distortion spotted in deep-field telescope images, a smudge of light that didn't align with any known massive object. Could that be a dark star bending the light of galaxies billions of years behind it? The math is tantalizing. A dark star's unique composition, lacking the blazing heat of fusion but packed with dense dark matter, would create a subtler, more diffuse lensing effect than a black hole. It wouldn't snap light into sharp rings or stark duplicates. Instead, it might stretch background starlight into eerie, faint arcs like shadows cast by something just out of view. And then there's the timing. Some lensing events flicker unpredictably, as if the object causing them is shifting in ways we don't expect. A black hole's gravity is relentless and stable, but a dark star, its core, powered by the annihilation of dark matter, might fluctuate as particles collide and decay, subtly changing its gravitational grip over time. Picture a star that breathes not in light but in gravity itself, pulsing gently as it consumes its invisible fuel. If we could catch one of these variations in the act, it might be the clue that separates a dark star from the cosmic background noise. The hunt is already underway. Telescopes like the James Webb Space Telescope are scanning the oldest, dimmest corners of the universe, searching for anomalies that don't fit the known catalog of celestial objects. Every odd lensing event, every unexplained warp in spacetime is a potential lead, but finding a dark star isn't just about adding another wonder to the cosmos, it's about rewriting what's possible. If these gravitational ghosts are real, they'd prove that stars can thrive without fire, that darkness can shape the universe as powerfully as light, and that even our most advanced instruments are still just scratching the surface of the unknown. For now, these phantom stars remain just beyond our grasp, bending light in ways we're only beginning to decode. But with every new anomaly, every unexplained twist in the sky, we get closer to answering the most thrilling question of all. How many more cosmic secrets are hiding in plain sight, waiting for us to see them not with our eyes but through the warped mirror of gravity itself? In the darkest reaches of space, some monsters wear masks. Take quasars, those brilliant beacons powered by supermassive black holes devouring entire stars. Their searing radiation makes them visible across billions of light years. But what if some of these cosmic lighthouses aren't what they seem? Imagine a quasar that doesn't shine. A phantom, a dark star so massive it mimics a black hole's hunger, warping its surroundings with such ferocity that gas clouds spiral toward it, heating to incandescent fury. Yet the star itself remains cloaked in shadow, its core burning not with starlight, but with the silent annihilation of dark matter. This is the enigma of the phantom quasar. From a distance, it ticks all the boxes, swirling accretion disks, superheated plasma jets, even the telltale X-ray signatures we associate with feeding black holes. But peer closer and the illusion unravels. A true quasar's light comes from its blazing disk of doomed matter, vaporizing as it crosses a black hole's event horizon. A dark star, though, has no horizon, just an unfathomably dense core where dark matter particles collide and vanish. The light we'd see wouldn't come from the star itself, but from the chaos it creates. Picture a whirlpool in space where gas clouds ripped apart by tidal forces glow like embers in a cosmic forge, while the dark star at the center remains as invisible as a silhouette cut from the fabric of the universe. Astronomers might have already catalogued these imposters without realizing it. Some quasars behave oddly. Their energy output fluctuates in ways that don't quite match black hole models, or their spectra show unexpected gaps where certain wavelengths simply drop out. One explanation: we're not seeing a black hole's feast, but the death throes of matter spiraling toward something even stranger. A dark star's gravity would be strong enough to shred gas clouds, but its lack of a traditional event horizon means some material might escape in erratic bursts, creating flickers that defy prediction. Then there's the question of scale. The largest known quasars anchor galaxies, their black holes weighing billions of suns, but dark stars could theoretically grow even larger, their mass ballooning as they feed on dark matter. A phantom quasar might not just mimic a black hole, it could overshadow one, its gravitational influence stretching farther than physics should allow. We've observed quasars in the early universe so colossal that they challenge our models of how black holes grow so quickly. Could some of them be dark stars instead, born already monstrous from the ashes of the cosmos' first moments? The key to unmasking these phantoms lies in their whispers. Black holes announce their presence with X-rays and gamma rays as matter accelerates to near light speed. A dark star would leave a quieter signature, subtle ripples in the cosmic microwave background, or faint distortions in the paths of nearby stars. New telescopes designed to map dark matter's invisible web might finally spot these anomalies, not by catching them in the act of destruction, but by sensing the void they carve in the darkness. Until then, the phantom quasars linger at the edge of discovery, taunting us with their cosmic masquerade. They challenge not just what we see, but how we see. If a star can hide in plain sight, bending the universe's rules to its will, what else have we missed? Every unexplained flicker, every oddity in the data could be a clue, or a dark star laughing silently in the void, waiting for us to finally understand the truth. Some of the most fascinating cosmic dances happen when stars pair up. Binary systems where two stars orbit a shared center of gravity are common across the galaxy, but what if one of those partners refuses to take the spotlight? Picture a celestial waltz where one dancer shines brilliantly while the other moves in utter darkness, its presence betrayed only by the subtle, invisible pull it exerts on its luminous twin. This is the mystery of the dark binary, a star system where half the equation is missing, replaced by something far stranger. The concept isn't entirely hypothetical. Astronomers have long studied binaries where one star is faint like a white dwarf or neutron star, but a true dark binary would be different. Here, the invisible partner wouldn't just be dim. It would emit no light at all, its existence revealed solely through the wobbles and tugs it imposes on its visible counterpart. Think of it like a game of cosmic hide and seek, where the hidden player leaves fingerprints on the only clue we can see. These gravitational disturbances would follow predictable patterns. a rhythmic sway in the visible star's motion, or sudden, unexplained shifts in its velocity as it's jerked around by something unseen. Yet confirming such a system is anything but straightforward. Ordinary binaries announce themselves through paired light signatures, but a dark star's companion might masquerade as a lone wanderer. Even when its odd behavior raises suspicions, ruling out other explanations like an unseen black hole or rogue planet requires painstaking precision. Take the case of a star observed accelerating unpredictably across the sky. At first glance, it might seem like a candidate for a dark binary, but alternative explanations abound. Could it be hurtling through a dense patch of interstellar dust, or caught in the wake of a passing stellar cluster? Without direct evidence, the dark star hypothesis lingers in the shadows of uncertainty. The tools we use to hunt these phantoms are as ingenious as the hunt itself. Spectrographs dissect starlight into fine wavelengths, searching for the telltale redshift and blueshift of a star being tugged back and forth by an invisible partner. Astrometry maps stellar positions with microscopic precision, tracking deviations as small as a fraction of an arcsecond, equivalent to spotting a human hair from 10 miles away. And then there's timing. Pulsars, the ultra-dense spinning remnants of dead stars, act as cosmic metronomes. When their precise pulses falter, it often signals the gravitational nudge of a companion. But what if that companion isn't a planet or neutron star? What if it's something darker? The implications of finding a dark binary would ripple far beyond cataloging an oddity. It could redefine how we measure mass in the universe. Normally, astronomers calculate stellar masses by studying light and orbital dynamics, but a dark star's weight would have to be inferred purely through gravity's grip, offering a rare chance to study mass divorced from light. Even more tantalizing, if dark stars exist, their binaries might reveal how they interact with normal matter over cosmic time. Do they collide, merge, or simply orbit eternally, one half of the pair forever unseen? For now, the dark binary remains a specter in the data, a plausible answer to anomalies we can't yet explain. Every unexplained stellar wobble, every erratic pulse from a distant star could be a clue, or it could be another dead end in a universe that delights in hiding its deepest secrets. But that's the thrill of the hunt, because if we ever confirm a star dancing with nothingness, it won't just solve a mystery. It'll force us to ask what else we've been missing in the vast, uncharted dark. Most stars belong to something: a galaxy, a cluster, a system. But what if some choose exile? Picture a dark star cast adrift, untethered from the cosmic structures we take for granted, sailing through the void like a ghost ship in the endless night. This isn't just a wandering oddity. A rogue dark star drifting far from the gravitational anchors of galaxies could hold clues to mysteries we've barely begun to unravel. The key lies in how it got there. In a universe where gravity rules, escaping a galaxy's pull requires unimaginable force. One possibility: a cosmic slingshot. Imagine two galaxies colliding, their gravitational chaos flinging stars outward like sparks from a fire. Most are ordinary stars, bright enough to track. But a dark star, invisible and unfathomably dense, might be hurled into the abyss without a trace except for the wake it leaves in the fabric of space itself. Detecting such an outcast wouldn't rely on light. Instead, astronomers would hunt for the subtle warping of space-time in places where nothing visible exists to cause it. Gravitational microlensing, the same phenomenon that bends light around massive objects, could reveal a rogue dark star's passage as it drifts between us and distant stars. The telltale sign: a brief, unexplained brightening of a background star, as if an unseen lens focused its light for a moment before vanishing back into the dark. But the real revolution wouldn't just be spotting one. It's what these loners could tell us about dark matter itself. If rogue dark stars exist, their distribution across the cosmos would map the invisible scaffolding of the universe. Dark matter isn't spread evenly, it clumps in filaments and halos, weaving a hidden web that guides the formation of galaxies. A lone dark star, floating far from any visible structure, would be a breadcrumb leading us to the untouched stretches of this web, places where dark matter's purest behavior isn't muddled by the interference of ordinary matter. And then there's the question of survival. A dark star untethered from a galaxy's resources would have to sustain itself on the sparse dark matter drifting through interstellar space. Could it? If so, it would force us to rethink how dark matter interacts with itself, whether it clumps densely enough to fuel such a star indefinitely, or whether these rogues are cosmic dead men walking, slowly starving in the void. The hunt is already yielding tantalizing maybes. Some microlensing events defy explanation, their signatures too prolonged or asymmetrical to match known objects. Could these be the fingerprints of rogue dark stars passing like phantoms through our observational net? Each unexplained flicker is a thread to pull, a potential window into the dark universe's most elusive architects. Finding one would do more than add a curious entry to astronomy's catalogue. It would prove that dark matter can sculpt the cosmos on its own terms, creating structures that dance to an entirely different tune. And if these loners drift through the darkness in numbers, they could be the missing piece in our understanding of why the universe looks and behaves the way it does. Until then, they remain ghosts in the data, silent travelers in the night, waiting for us to ask the right questions. At the heart of nearly every galaxy, astronomers find the same cosmic monster, a supermassive black hole, millions or even billions of times heavier than our Sun. These gravitational behemoths anchor their galaxies, their immense pull dictating the motions of stars around them. But what if some of these monsters aren't black holes at all? What if, hidden in plain sight, a dark star lurks at the center, mimicking a black hole's grip so perfectly that we've been fooled all along? The idea isn't as far-fetched as it sounds. A dark star with enough mass would warp space-time identically to a black hole of the same weight. From a distance, the two would be nearly indistinguishable. Both would bend light, accelerate nearby stars to dizzying speeds, and even generate swirling accretion disks of superheated gas. But dig deeper and the differences emerge. A black hole's event horizon is a point of no return, a boundary where even light vanishes. A dark star, though, would have no horizon. Instead, its core might pulse with the slow burn of dark matter annihilation, a process invisible to our telescopes but capable of producing the same crushing gravity. This raises a tantalizing question. Could some of the objects we've labeled as supermassive black holes actually be dark stars in disguise? Take Sagittarius, a star, the beast at the center of our own Milky Way. We've mapped stars whipping around it at thousands of miles per second, their orbits betraying the presence of something 4 million times the mass of our Sun. But what if that something isn't a black hole's singularity? What if it's a dark star's unfathomably dense core, radiating nothing but gravity? The distinction matters because dark stars could solve one of astrophysics' lingering puzzles: how supermassive black holes grew so large so quickly. In the early universe, some appeared fully formed when the cosmos was less than 1 billion years old, leaving astronomers scratching their heads over how they had enough time to feast on surrounding matter. A dark star offers a shortcut. Born already colossal from the collapse of primordial dark matter clouds, it wouldn't need to slowly accumulate mass. It would start as a titan, its gravity immediately shaping the galaxy around it. Yet proving this hypothesis is a monumental challenge. Without light or radiation to study, how do we tell a dark star apart from a black hole? The answer might lie in the details of their gravitational influence. A black hole's pull is clean, predictable. A dark star's could fluctuate slightly as dark matter particles within it collide and decay, creating subtle hiccups in the orbits of nearby stars. Or there might be hints in the way gas behaves at the brink of oblivion. Near a black hole's event horizon, matter stretches into spaghettified strands before vanishing. Near a dark star, some material might rebound, ejected by shock waves from dark matter reactions, creating faint echoes in X-ray or radio waves. For now, the galactic core imposter remains a shadow in our theories. But with next-generation telescopes probing deeper into the hearts of galaxies, we might soon spot the anomalies that betray its presence. Every unexplained wobble in a star's path, every odd flicker from a galactic center, could be a clue, a whisper from the darkness that reshapes our understanding of the universe's most powerful engines. And if we find even one, it won't just rewrite the story of black holes. It'll force us to reconsider what else might be hiding in the cosmic shadows, masquerading as something we thought we knew. Time doesn't flow evenly across the cosmos. It bends, stretches, and twists under the weight of massive objects. Now, imagine a dark star so colossal that its gravity doesn't just warp space but time itself. Near its surface, seconds could crawl like hours, light stretching into whispers, and the very fabric of reality distorted beyond recognition. This isn't just theoretical. Einstein's equations predict that extreme mass slows time, and a dark star of sufficient size would warp the universe around it in ways even black holes can't match. The most startling evidence of this time-warping effect might be hiding in the oldest light we can observe, the cosmic microwave background. This faint glow, left over from the universe's infancy, blankets the cosmos like a fossilized echo of the Big Bang. But if a primordial dark star existed early enough, its gravitational grip could have left subtle fingerprints in that radiation. Picture a dark star drifting through the young universe, its immense gravity stretching space-time like a dent in fabric. Light passing near it would have been redshifted or blueshifted, creating tiny temperature fluctuations in the microwave background, anomalies that linger like shadows long after the star itself has vanished. These imprints wouldn't look like anything else. Dark matter's unique properties mean a dark star's gravitational well would be more diffuse than a black hole's, warping the cosmos in a broader, smoother pattern. Instead of sharp distortions, we'd find gentle ripples in the microwave background, regions slightly cooler or warmer than their surroundings, as if the universe itself bore the memory of an ancient encounter with something unimaginably heavy. Some of these anomalies have already been spotted. The Planck satellite's maps of the cosmic microwave background reveal unexplained hot and cold spots, areas where the radiation doesn't align with standard models of the early universe. Could these be the faint echoes of dark stars, their time-bending gravity frozen into the sky? But the implications go deeper. If dark stars warp time enough, they might create cosmic time capsules, regions where the universe's clock ticks slower, preserving conditions from earlier epochs. Gas clouds near such a star could appear chemically primitive, their elements untouched by billions of years of stellar evolution. Even more bizarre, a dark star's time dilation could distort our observations of distant galaxies. Light emitted from behind one might reach us slowed, making those galaxies seem older or younger than they truly are, like cosmic mirages warped by an invisible lens. The hunt for these time-warping leviathans is already reshaping how we study the early universe. New telescopes designed to map the cosmic microwave background in unprecedented detail could uncover patterns that betray a dark star's passage. Others might spot galaxies with inexplicable age discrepancies, their light bent not just in space but in time. Each anomaly brings us closer to answering a haunting question. Did the universe's first monsters leave scars not just on space but on time itself? And if so, what else have we been missing in the slow, silent dance of the cosmos? A star's death is usually a spectacular light show, supernovas outshining entire galaxies, neutron stars pulsing like cosmic lighthouses, black holes swallowing matter in bursts of X-rays. But what if a star could die in total silence? No blinding flash, no shockwave of radiation, just the universe itself shuddering under the weight of its collapse. This is the dark supernova, a theorized end for dark stars, where their demise wouldn't light up the sky but would instead send ripples through the very fabric of spacetime. Picture a dark star reaching the end of its life. Unlike ordinary stars, its core hasn't been powered by nuclear fusion, but by the annihilation of dark matter particles. As that fuel runs out, gravity takes over, crushing the star inward with unstoppable force. But here's where physics takes a strange turn. Without the explosive rebound of a traditional supernova, no fiery shockwave to blast away its outer layers, the dark star's collapse would be eerily quiet. No light, no radiation, just an implosion so violent it warps spacetime itself, sending gravitational waves spiraling outward at the speed of light. These waves wouldn't be subtle. A dark star massive enough to avoid collapsing into a black hole, yet dense enough to tear apart the space around it, could generate gravitational surges detectable across the universe. Think of dropping a boulder into a still pond. The splash is the visible supernova. The dark supernova skips the splash entirely, but the ripples, those would be colossal. And we've already built machines to catch them. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory, whose ultra-sensitive detectors have been listening to the cosmos whispers since 2015. LIGO greatest hits so far include mergers of black holes and neutron stars, each event producing a distinct gravitational wave signature, a cosmic chirp that rises in pitch before cutting off abruptly. But a dark supernova would sound different. Instead of a quick merger chirp, the waveform might resemble a slow, drawn-out crescendo as the star's core buckles unevenly, its dark matter components collapsing in waves rather than all at once. Some theorists suggest these events could even produce low-frequency rumbles too long for LIGO current design to catch, a bass note in the universe's symphony, waiting for future observatories like LISA, the space-based gravitational wave detector, to tune in. The real challenge, telling a dark supernova apart from other cosmic catastrophes. When LIGO detects a gravitational wave, astronomers scramble to find a matching flash of light, a neutron star collision's gamma-ray burst, for example. But with a dark supernova, there'd be nothing to see. Just an inexplicable tremor in spacetime unaccompanied by any electromagnetic signature. That's the ghost we're hunting, an anomaly in the data that defies every expected pattern. And the clues might already be hiding in plain sight. LIGO catalog includes several detections that don't neatly match known phenomena, events with waveforms slightly too prolonged or asymmetrical to be black hole mergers. Could one of these be the first recorded dark supernova, without a light-based counterpart, confirming it would require piecing together indirect evidence, the wave's frequency, duration, even the direction it came from? A dark supernova might originate in regions of space where dark matter is unusually dense, or from an era when primordial dark stars were more common. Cross-referencing gravitational wave data with dark matter maps could turn a maybe into a revelation. What's at stake isn't just adding a new explosion type to the cosmic ledger. If dark supernova exist, they'd prove that dark matter can gather, ignite, and die in ways we've never witnessed, offering a glimpse into its fundamental nature. Do dark matter particles annihilate cleanly, or do they leave behind exotic remnants? Does their collapse seed new black holes, or could dark stars vanish entirely, leaving only gravitational echoes behind? Every unexplained ripple in LIGO data is a thread to pull, leading us deeper into the dark universe's best-kept secrets. The hunt is only beginning. As gravitational wave astronomy matures, our detectors will grow more sensitive, capable of hearing fainter, stranger events. And somewhere out there, in the silence between the stars, a dark supernova might be waiting, its story written not in light but in the twisting of spacetime itself. All we have to do is listen. Scattered across the cosmos, most nebulae announce themselves in bursts of color, glowing clouds of ionized gas lit up by nearby stars. But what if some of these cosmic tapestries don't glow at all? Imagine a nebula so dark it doesn't just hide in the void, it bends the rules of how matter and light interact. This isn't science fiction. It's the invisible nebula, a vast shroud of dark matter particles swirling around a dark star, so diffuse and elusive that it slips past our telescopes entirely. The concept challenges everything we know about how nebulae form. Ordinary stellar nurseries are sculpted by radiation and stellar winds, their intricate shapes visible in vibrant hues. A dark nebula, though, would be shaped by something far more subtle, the gravitational whispers of dark matter. Without light to push it around, this shadowy cloud wouldn't form delicate filaments or dramatic pillars. Instead, it might stretch into a sprawling, uneven halo, its structure dictated purely by the dance between the dark star's gravity and the mysterious particles it's made of. The real puzzle: how to detect something that refuses to be seen. Traditional astronomy relies on light photons hitting our telescopes, but a dark nebula's particles interact so weakly with light that they might as well be ghosts. Yet scientists have devised ingenious ways to hunt for these phantoms. One approach leverages cosmic rays, high-energy particles bombarding Earth from space. As these rays pass through a dark nebula, a fraction might collide with its hidden particles, producing telltale gamma rays or antimatter signatures. Telescopes like the Fermi Gamma Ray Space Telescope scan the skies for these anomalous bursts, searching for patterns that could betray the presence of an invisible structure. Then there's gravitational lensing. Just as a dark star warps light passing near it, an entire nebula of dark matter would distort the images of background galaxies on a grander scale. Instead of sharp arcs or rings, the effect would be subtler, a gradual smearing of starlight, as if the cosmos itself were slightly out of focus in one spot. Astronomers have already mapped strange, unexplained lensing anomalies in regions where no visible matter seems to account for the distortion. Could these be the fingerprints of dark nebulae, their mass-bending spacetime without a single glowing atom to give them away? The most tantalizing clues might come from the dark star at the nebula's heart. If the star emits even a faint whisper of radiation, perhaps from stray particles colliding at its edges, it could create a target for infrared or radio telescopes. Picture a cold, diffuse glow at wavelengths where dark matter's interactions might leave a trace. Experiments like the James Webb Space Telescope's Deep Field surveys aren't just looking for galaxies, they're scanning for irregularities in the infrared background, tiny fluctuations that could hint at vast, unseen structures. But the ultimate test might rely on particle physics itself. If dark matter particles occasionally annihilate upon contact, as some theories suggest, a dark nebula could be a factory for exotic byproducts, neutrinos, for instance, which travel unimpeded through space. Detectors like IceCube, buried deep in Antarctic ice, await these elusive particles, hoping to trace their paths back to hidden cosmic engines. A cluster of neutrinos arriving from a seemingly empty patch of sky could be the smoking gun, pointing to a dark nebula's silent fireworks. The search is a testament to how far astronomy has come. We're no longer limited to studying what shines. Instead, we're learning to read the universe's hidden language, the gravitational nudges, the ghostly particles, the quiet distortions in the fabric of reality. Every unexplained signal, every anomalous ripple, brings us closer to unmasking one of the cosmos' best-kept secrets. And if we find even one dark nebula, it won't just be a discovery. It'll be a revolution, a proof that the universe we see is only the faintest echo of the universe that's truly there. Deep in the void where light dares not travel, another kind of force could be at work, one that twists the paths of particles like an invisible hand. Picture a dark star, not just massive and cold, but wrapped in a magnetic field so powerful it rivals the most extreme objects in the universe. This isn't just a star that hides in darkness, it's a cosmic powerhouse, bending the very rules of physics around it without emitting a single photon of light. Magnetism on this scale defies imagination. The average neutron star's magnetic field is strong enough to rip atoms apart from thousands of miles away. But a dark star's field could be orders of magnitude stronger, generated not by spinning charged particles like ordinary stars, but by the turbulent, unseen interactions of dark matter itself. Imagine a dynamo buried in the star's core, where exotic particles collide and spin, weaving magnetic threads through space like an unseen spider's web. Charged particles straying too close wouldn't just veer off course, they'd be whipped into frenzied spirals, accelerated to near-light speeds before being hurled into the void like cosmic bullets. These magnetic maelstroms might solve one of astronomy's oldest riddles, the origin of ultra-high-energy cosmic rays. These subatomic particles, streaking through space with energies far beyond anything human-made colliders can produce, have puzzled scientists for decades. Some come from supernova or active galaxies, but others arrive with no clear source, as if launched from something invisible. A dark star's magnetic field could be the ultimate particle accelerator. Picture a lone proton caught in the star's grip, spun faster and faster along magnetic field lines until it's flung outward with unimaginable force. Unlike pulsars, which fire radiation in predictable beams, a dark star's ejections could be chaotic, spraying particles in all directions, leaving no luminous trail to trace them home. The evidence might already be hiding in our data. Cosmic ray detectors have recorded particles with trajectories bending back toward seemingly empty patches of sky areas where no known magnetar or black hole resides. Some even carry energy signatures that don't match typical astrophysical models. Could these be the fingerprints of a dark star's magnetic fury, its invisible tendrils reaching across the galaxy to touch us? The challenge is connecting the dots. Without visible counterparts, researchers must rely on statistical anomalies, clusters of high-energy particles arriving from the same general direction, or odd fluctuations in Earth's atmospheric showers that suggest something massive and magnetized lurks beyond our sight. Yet the implications stretch beyond cosmic rays. If dark stars harbor such intense magnetism, their influence could warp entire regions of space. Gas clouds drifting nearby might be shredded into swirling plasma vortices, their atoms ionized by unseen forces. Passing stars could have their stellar winds twisted into bizarre, glowing halos not from the dark star's light, but from the violent interplay between its magnetic field and their own charged particles. Even time itself might behave strangely in its vicinity, as relativistic effects from accelerated matter warp local space-time. The hunt for these magnetic phantoms is pushing our instruments to their limits. New generations of cosmic ray observatories, like the Pierre-Auger array, are mapping particle arrivals with unprecedented precision, searching for patterns in the chaos. Meanwhile, radio telescopes scan the skies for the faintest whispers of synchrotron radiation, the telltale emission of electrons spiraling in magnetic fields that might hint at an invisible source. Every unexplained detection edges us closer to a startling possibility that the universe's most powerful particle accelerators aren't the brilliant quasars or colliding galaxies we can see, but the dark stars we've yet to find. What's at stake isn't just another entry in the catalog of cosmic oddities. If these magnetic monsters exist, they'd force us to rewrite the rules of how magnetic fields form and evolve. They'd challenge our understanding of dark matter's behavior under extreme conditions, proof that it doesn't just clump passively, but can generate forces that shape the cosmos. And most tantalizing of all, they might finally answer why some particles race across the universe with energies that defy explanation, as if fired from a gun we've never seen. Until then, the mystery lingers, a shadow in the data, a whisper in the void waiting to be heard. Gravity weaves its threads not just around single stars, but across entire cosmic gatherings. And when those gatherings are made of dark stars, the result is something truly extraordinary. Imagine a cluster of these invisible giants drifting through the void like a ghostly archipelago. their combined mass warping the space around them so profoundly that distant galaxies appear stretched and twisted like reflections in a funhouse mirror. This is no ordinary star cluster. This is a gravitational hall of mirrors where the unseen exerts its pull on everything that passes by. The concept isn't just theoretical. Astronomers have long studied how massive objects bend light, but a dark star cluster would take this phenomenon to the extreme. Picture a group of 100 or 1,000 dark stars, each weighing hundreds of times more than our Sun, orbiting one another in slow, silent harmony. Their combined gravity would create a lensing effect far more complex than a single star could produce. Light from galaxies behind them wouldn't just bend around individual stars, it would twist into intricate patterns like ripples in a pond disturbed by countless unseen stones. Some background stars might appear multiplied, their light split into several faint copies. Others could stretch into long, luminous arcs, smeared across the sky by the cluster's collective pull. Finding such a cluster wouldn't be as simple as spotting a single lensed galaxy. The telltale signs would be subtler statistical anomalies in the way distant light is distorted. Surveys like the Hubble Space Telescope's frontier fields have already mapped regions where gravitational lensing seems stronger than visible matter can explain. In some cases, the distortion isn't centered on a galaxy or black hole, but on nothing, just empty space tugging at the fabric of reality. Could these be the fingerprints of a dark star cluster, its members too diffused to see yet massive enough to twist the cosmos around them? The key lies in the patterns. A single dark star might create a simple arc or duplicated image. A cluster would produce something far more chaotic, a patch of sky where lensed galaxies seem to swirl around an invisible vortex, their distortions overlapping in ways that defy simple explanation. Computer simulations suggest these clusters could even mimic the effects of dark matter halos, those vast, invisible cocoons thought to surround galaxies. But unlike halos, which spread matter smoothly, a dark star cluster's lensing would have a granular texture, its distortions flickering slightly as the stars within it shift position over centuries. And then there's the question of how such a cluster could form in the first place. Ordinary star clusters emerge from collapsing gas clouds, but dark stars would need a different cradle. One possibility, the early universe where dense patches of dark matter could have pooled together like ink in water, collapsing directly into dark stars without ever igniting into light. Over time, gravity would herd these stars into groups, their mutual attraction outweighing the expansion of space itself. If they exist, these clusters could be relics of a time before galaxies, ancient structures that predate even the first flickers of starlight. The hunt for these invisible archipelagos is pushing astronomy to its limits. New tools like the Vera-C, Rubin Observatory, with its ability to scan the entire sky every few nights, could catch the fleeting distortions caused by dark star clusters drifting across our line of sight. Meanwhile, gravitational wave detectors might one day sense the subtle ripples produced as these stars orbit one another, their silent dance reverberating through space-time. What's at stake isn't just another entry in the catalogue of cosmic curiosities. If dark star clusters exist, they'd be proof that dark matter can clump and congregate in ways we've never witnessed, forming structures entirely separate from the luminous universe we know. They'd challenge our models of how gravity shapes the cosmos on the largest scales, forcing us to ask, how much of the universe's architecture is built not from stars and gas, but from shadows we've yet to see? The answer might be written in the warped light of distant galaxies, waiting for us to decode its secrets. At the very edge of what physics allows, where matter and gravity twist the rules beyond recognition, there could exist a dark star unlike any other. Not just massive, not just invisible, but teetering on the brink of quantum impossibility. This is the quantum singularity dark star, a celestial paradox where the crushing weight of dark matter collides with the bizarre laws of the subatomic world. Picture a star so dense that particles inside it don't behave like particles at all, but like waves flickering in and out of existence, their positions uncertain, their very reality blurred by the extremes of gravity. Here, the boundary between star and black hole doesn't just fade, it shatters. The key lies in the Planck scale, the smallest measurable unit in the universe, where space and time stop being smooth and instead churn like a quantum foam. Under normal circumstances, this chaos is invisible, hidden far below the scales we can observe. But inside a quantum singularity dark star, the sheer density of dark matter could magnify these effects, stretching them to macroscopic scales. Imagine a core where particles tunnel through barriers they shouldn't, where entanglement links one side of the star to the other instantaneously, and where gravity itself fluctuates in strange, unpredictable pulses. This isn't just a star with quantum properties, it's a star where quantum weirdness becomes the dominant force, rewriting the rules of how matter collapses under its own weight. What would that look like to an outside observer? Almost nothing. And that's the chilling part. Unlike a black hole which announces itself with an event horizon, a quantum singularity dark star might have a fuzzy surface, a region where the very concept of a boundary breaks down. Light escaping from near its edges could arrive scrambled, its wavelength stretched and twisted by quantum gravity effects. Matter falling toward it wouldn't simply vanish. It might seem to stutter, flickering in and out of visibility as it interacts with the star's unstable spacetime. Even time near its surface could become erratic, flowing unevenly like a river caught in a storm. Theorists have speculated about such objects for decades, often dismissing them as mathematical curiosities. But recent advances in quantum gravity, particularly in loop quantum cosmology and string theory, suggest they might not be so far-fetched after all. Some models predict that under the right conditions, collapsing dark matter could reach a point where quantum pressure counteracts gravity, preventing a full collapse into a black hole. Instead, you'd get something suspended between states, not quite a star, not quite a hole, but a quantum relic-defying classification. The implications ripple outward. If these stars exist, they could be cosmic laboratories for physics we've only dreamed of testing. Their cores might generate spontaneous bursts of virtual particles, offering glimpses into how matter behaves at energies trillions of times higher than any collider could produce. They could even emit faint, distinctive radiation, hawking like evaporation but twisted by dark matter's unique properties, creating a signal unlike anything else in the universe. Telescopes searching for anomalies in the cosmic microwave background or unexplained high-energy photon showers might already have recorded these echoes without realizing what they were. Yet the greatest mystery isn't how to find them, it's what their existence would mean for our understanding of reality. A quantum singularity dark star wouldn't just challenge our models of stars or dark matter. It would force us to confront the messy intersection of quantum mechanics and general relativity, the holy grail of modern physics. Is spacetime fundamentally smooth, or is it granular at the tiniest scales? Can gravity and quantum forces truly coexist, or do they break down into something entirely new under extreme conditions? These stars could be the key, or they could be the universe's way of telling us we're asking the wrong questions altogether. For now, they linger at the edge of theory and observation, ghostly reminders of how much we still don't understand. Every unexplained signal, every odd gravitational ripple could be a clue, or a red herring in a cosmos that delights in keeping its deepest secrets. But if we ever prove their existence, it won't just be a discovery. It'll be a revolution, revealing a universe far stranger, far more malleable than we ever dared to imagine. Long before the first galaxies took shape, when the universe was just a seething sea of raw energy and exotic particles, something extraordinary may have formed in the chaos, a relic so ancient it carries whispers of creation itself. This isn't just a dark star, it's a cosmic time capsule forged from the primordial ingredients of the Big Bang and frozen in a state unchanged for over 13 billion years. Imagine an object that doesn't just hide in darkness but preserves it, its very composition a snapshot of the universe's fiery birth. What makes this relic unique isn't just its age, it's what's inside. While later stars recycled heavier elements from generations of supernova, a primordial dark star would be built from particles that existed mere moments after the Big Bang. WIMP actions or other exotic dark matter candidates that vanished from the rest of the universe as it cooled. Locked away in its core, these particles could still interact as they did in the cosmos' infancy, offering physicists an unprecedented window into conditions we've only simulated in equations. Think of it like finding a vial of air from Earth's earliest atmosphere, except this vial is the size of a star, and its contents could rewrite the rules of particle physics. The real magic lies in how these relics could preserve the universe's earliest symmetries. Modern dark matter behaves differently than it did in the high-energy chaos of the Big Bang, just as water behaves differently as steam, liquid, or ice. But inside a primordial dark star crushed by unimaginable gravity, those ancient symmetries might still hold. Collisions in its core could replicate energies seen nowhere else in the modern universe, sparking reactions that produce particles long thought extinct. If we could study even one such event, it might reveal why dark matter dominates the cosmos' mass yet refuses to interact with light, a mystery that's eluded scientists for decades. Astronomers are already scanning the skies for clues. The James Webb Space Telescope's infrared eyes are perfect for spotting anomalies in the oldest, most distant regions of space, places where the universe's first structures flickered to life. A relic dark star wouldn't glow like a quasar or galaxy, but its gravity would leave subtle imprints on the cosmic microwave background, warping the afterglow of the Big Bang like a fingerprint pressed into cooling wax. Some theorists even suggest these stars could cast cold shadows in the microwave background, patches slightly cooler than their surroundings where the relic's gravity subtly redshifted passing photons billions of years ago. Yet the greatest challenge is proving such a star isn't just another black hole or cold gas cloud. The telltale sign might lie in its movement. Born before galaxies had fully formed, a primordial relic wouldn't orbit a galactic center like modern stars. It would drift through intergalactic space like a ghost ship, its trajectory untouched by the gravitational tug of war shaping younger cosmic structures. If we found an object with the mass of a star but the motion of a wanderer, it could be the smoking gun. Discovering one of these relics wouldn't just add to the celestial bestiary. It would be like unearthing a Rosetta Stone for the early universe, translating the cryptic language of the Big Bang into something we can finally understand. Every flicker in its core, every ripple in spacetime around it, would carry echoes of a time when the cosmos was young, hot, and teeming with possibilities long since vanished. And somewhere out there, in the vast darkness between galaxies, one of these ancient timekeepers might still linger waiting to tell its story. Most stars pulse with light, but in the silent depths of space, something far stranger might be ticking like a cosmic metronome, not with beams of radiation, but with ripples in the fabric of spacetime itself. This is the dark pulsar, a spinning dark star so dense and massive that its rotation warps the universe around it, sending out gravitational waves in perfect rhythmic bursts. Unlike its luminous cousin, the neutron star pulsar, this invisible titan doesn't blink with electromagnetic radiation. Instead, it thrums, an endless drumbeat of gravity waves cascading through the cosmos, detectable only by the most sensitive instruments humanity has ever built. The key to its rhythm lies in its imperfections. Even a perfectly smooth sphere, if spun fast enough, would distort spacetime, but a dark pulsar wouldn't be perfectly smooth. Imagine a mountain range, not of rock but of densely packed dark matter stretching across its surface. As the star rotates, these mountains churn the space-time around them, creating gravitational disturbances that propagate outward like ripples from a stone tossed into a pond. The result, a signal as precise as a clock, pulsing at intervals that could range from milliseconds to hours depending on the star's size and spin. This isn't just theoretical. Gravitational wave observatories like LIGO and Virgo have already detected the chaotic crashes of black holes and neutron stars. But dark pulsars would offer something different, a clean, repeating signal, almost musical in its regularity. Existing pulsar timing arrays networks of radio telescopes that track the incredibly stable spins of neutron stars might already hold clues, some anomalous timing residuals, tiny deviations in otherwise predictable pulsar beats could hint at the gravitational influence of a nearby dark pulsar tugging at spacetime as it spins. The real challenge is isolating the signal. Picture trying to hear a single violin in a symphony where all the other instruments are playing at random. Gravitational wave detectors are bombarded with noise from Earth's seismic murmurs to distant supernova. But dark pulsars have one advantage: their signals are predictable. Advanced algorithms comb through data, searching for repeating patterns buried in the cosmic static. If a candidate is found, the next step would be triangulation. Just as sailors once used lighthouses to navigate, scientists could trace the origin of these gravitational pulses by measuring minute differences in how they arrive at detectors across the globe or even in space, like the future LISA observatory. The implications of discovery would ripple far beyond cataloging another cosmic oddity. Dark pulsars could serve as unparalleled laboratories for testing general relativity under extreme conditions. Their precise pulses would act as probes for the warped spacetime around them, revealing whether Einstein's equations hold true near objects where dark matter's exotic physics dominate. Even more tantalizing, their formation could unlock secrets about the early universe. If dark pulsars exist, they might be remnants of a time when dark matter clumped differently, forming dense, spinning cores long before ordinary matter coalesced into stars. For now, the hunt is a waiting game. Every new gravitational wave detection, every anomaly in pulsar timing arrays, brings us closer to answering a haunting question. Is the cosmos humming with the echoes of invisible giants, their rhythms woven into the fabric of reality itself? And if we learn to listen, what else might we hear, far out in the depths of a swirling molecular cloud, where baby stars flicker to life amidst curtains of cosmic dust? Something far more ancient lurks unseen. This isn't just another stellar nursery, it's a hunting ground. Hidden within the chaos, a dark star drifts like a phantom, its immense gravity tugging at the gas and dust around it, sculpting the birth of new stars without ever revealing itself. Molecular clouds are supposed to be the cradles of light, places where collapsing gas ignites into brilliance. But here, in the shadow of this invisible giant, the rules bend in ways we're only beginning to understand. The camouflage is nearly perfect. Drifting through the dense, frigid expanse of the cloud, the dark star's presence is betrayed only by its gravitational fingerprints. Picture a river flowing downstream, except the water is interstellar gas, and the unseen boulder diverting its current is a dark star's pull. Stars forming nearby spiral into odd, lopsided orbits. Protostellar disks, which should be symmetrical, warp under invisible strain. Even the cloud itself might appear oddly distorted, as if an enormous hand were pressing into it from the void. These aberrations aren't random. They're the subtle signature of something massive hiding in plain sight. Infrared astronomy could be the key to unmasking this cosmic ghost. While optical telescopes see only the clouds obscuring dust, infrared light pierces through, revealing the heat signatures of young stars, and critically, the absence where there should be presence. Imagine scanning a thermal image of a forest and spotting a patch of unnaturally cold air, a void where no living thing radiates warmth. That's what an infrared survey might find, a region where the dust is too cold, too undisturbed, as if something were siphoning away the energy needed for star formation. Even stranger, the surrounding gas might show unexpected temperature spikes, heated by turbulence as the dark star's gravity churns the cloud like a spoon in thick soup. Some of the best evidence might come from failed stars, brown dwarfs, objects too small to ignite fusion but too large to be planets, often form in molecular clouds. But in the grip of a dark star's influence, their distribution could become bizarrely skewed. Picture a game of cosmic pinball where the unseen player tilts the table. Brown dwarfs might cluster in odd configurations, or their orbits could trace the contours of an invisible gravitational well. Telescopes like the James Webb Space Telescope, with its unmatched infrared sensitivity, are already spotting anomalies in star-forming regions that defy standard models. Could some of these outliers be the handiwork of a dark star's invisible touch? The implications ripple far beyond a single hidden object. If dark stars silently shape stellar nurseries, they could explain why some clouds produce fewer stars than predicted, or why certain young stars move with inexplicable velocity. They'd be the unseen architects of star formation, their gravity weaving patterns into the cosmos long before light takes hold. And if we learn to read those patterns, we might uncover a hidden population of these shadowy titans, each one a relic from a time when the universe's first structures were built not from fire but from darkness. The hunt is already rewriting how we observe the sky. Every molecular cloud scanned, every anomalous temperature gradient mapped, brings us closer to answering a haunting question: how much of what we call empty space is actually threaded with the invisible threads of dark stars? And if they're out there, waiting in the dust, what other secrets might they be hiding? A solar system doesn't need sunlight to exist, just gravity. Picture a dark star adrift in the void, its invisible bulk anchoring something even stranger, a planet sculpted entirely from dark matter. This isn't a world of rock or ice, but a sphere of particles that refuse to interact with light, orbiting a star that itself emits no glow. A dark companion for a dark star, hidden so perfectly that its existence might only be betrayed by the way it warps the fabric of space around it. The concept upends everything we know about planets. Ordinary worlds form from the leftover debris of stellar birth, clumping together in disks of dust and gas. But a dark matter planet would have a far stranger origin story. Imagine a dense knot of dark matter, drawn together by its own gravity in the early universe, circling a dark star like a shadow bound to a shadow. Without light or heat to give it away, this world would be undetectable by any traditional means: no reflected starlight, no atmospheric signatures, not even a whisper in the radio spectrum. Yet its presence could ripple outward, bending the paths of distant stars and galaxies in ways that defy explanation. The key to unmasking these phantom worlds lies in a phenomenon called microlensing. When an invisible object passes between us and a distant star, its gravity acts like a magnifying glass, briefly amplifying the background star's light. Astronomers have used this trick for decades to spot rogue planets and faint brown dwarfs, but a dark matter planet's signature would be unlike anything in the catalogue. Unlike solid bodies, which create sharp, predictable lensing events, a dark matter world's diffuse structure might produce a smoother, longer distortion, like passing a finger through a candle's flame versus a piece of paper. The star behind it wouldn't just brighten and fade, its light might flicker oddly, as if strained through an invisible sieve. Even stranger, the planet's orbit around its dark star could leave a trail of clues. Most microlensing events are one-off occurrences, but a dark companion's repeated passes would create periodic ripples in the light of background stars. Imagine watching a street lamp through a slowly rotating fan. The flickers would follow a rhythm, a cadence tied to the unseen blades. Similarly, if astronomers spotted a distant star dimming and brightening on a strict timetable, it could signal an invisible clockwork system, a dark star and its shadowy world circling each other in perfect silent harmony. The hunt for these duets is already yielding tantalizing hints. Surveys like the optical gravitational lensing experiment have recorded microlensing events that don't fit the usual profiles, some too prolonged, others oddly asymmetrical. A handful even recur years apart, as if something massive and unseen is looping back into alignment with our line of sight. Could these be the footprints of dark companions, their gravitational nudges subtly rewritten the sky's map? The challenge is ruling out other explanations. A rogue ice giant drifting between stars or a neutron star's faint glow might mimic some of these effects. But as telescopes grow more precise, the anomalies that can't be explained by ordinary objects are piling up, and each one could be a thread leading to a darker truth. What's at stake isn't just adding another curiosity to the cosmic menagerie. If dark matter planets exist, they'd prove that dark matter can clump and structure itself on scales we've never imagined, forming entire worlds alongside stars in a parallel, unseen cosmos. They'd hint at a universe where dark matter isn't just a passive scaffold for galaxies, but an active participant in the dance of gravity. And they'd force us to ask an even more profound question. If dark stars can have dark planets, could those planets have dark moons, dark rings, dark atmospheres, if such a thing is possible? The possibilities spiral outward, rewriting the boundaries of what a world can be. For now, these phantom companions remain just beyond our reach, their presence felt but not seen. Yet with every unexplained flicker in the data, every rhythmic aberration in the light of distant stars, we edge closer to a revelation that the universe's hidden architecture might be far richer, far stranger than we ever dared to dream. Deep in the cosmic void, where the fabric of reality stretches thin, a dark star might not be drifting alone. It could be tethered to something far stranger, a flaw in the universe itself. Picture a cosmic string, a hypothetical filament of pure spacetime distortion, thinner than an atom yet denser than a mountain range, stretching across light years like an invisible wire. Now imagine one of these strings snagged on a dark star, its unimaginable tension pulling at the star's gravity like a bowstring drawn taut. The result: a gravitational anomaly unlike anything else in the cosmos, a dark star not just hidden in shadow, but warping the universe around it with impossible precision. Cosmic strings are relics of the early universe, theorized to have formed during the intense symmetry-breaking moments after the Big Bang. Think of them like cracks frozen in ice, remnants of a phase transition when the fundamental forces of nature split apart. Most models suggest these strings would drift undisturbed, but if one became entangled with a dark star, the interplay would be catastrophic. The string's near-infinite density would amplify the star's gravitational field, not just bending light around it but twisting spacetime into a funnel. A passing star or gas cloud wouldn't just veer slightly off course, it could be whipped into a spiral, accelerated to relativistic speeds before being flung into the void like a slingshot's payload. The strangest part, this partnership might leave clues in the cosmic microwave background. As the string vibrates, snapping like an unimaginably huge guitar string, it could generate gravitational waves with frequencies too low for current detectors to catch. But the dark star's presence would change that. The star's mass would act like a weight on the string, damping its vibrations into a lower, detectable range. Telescopes studying the microwave background might spot odd, linear disturbances, tiny, abrupt shifts in temperature aligned in perfect straight lines. These could be the echoes of a cosmic string's oscillations modulated by the dark star's grip. And then there's the motion. A dark star anchored to a cosmic string wouldn't move like other celestial objects. Instead of drifting smoothly through space, it might lurch in fits and starts as the string's tension yanks it forward like a puppet on a string. Over millennia, this erratic path could carve a visible wake in the interstellar medium, a trail of disturbed gas and dust pointing back to the invisible culprit. Astronomers mapping high-velocity clouds, enormous streams of gas racing through the galaxy, have occasionally found patterns that defy explanation. Could some of these be the scars left by a dark star and its cosmic tether, dragging through the cosmos like a ship's prow through water? The implications stretch beyond mere curiosity. If such a pairing exists, it could solve two mysteries at once. Cosmic strings, if real, would be direct evidence of the universe's earliest moments, a snapshot of physics operating at energies we can't hope to replicate. And a dark star entangled with one would give us a way to study both objects in tandem, a cosmic lab where gravity, dark matter, and space-time itself are pushed to their limits. Every unexplained gravitational ripple, every anomalous streak in deep space surveys, could be a breadcrumb leading us closer to this invisible duo. For now, the cosmic string anchor remains a specter in the equations, a tantalizing what-if lurking at the edge of discovery. But if we ever find it, the universe won't just seem stranger than we imagine, it'll be stranger than we can imagine, a place where the threads of reality itself knot around shadows in the dark. Some of the universe's most violent events announce themselves with blinding jets of radiation, quasars firing beams of energy across billions of light years, pulsars spinning out focused streams of particles. But what if the cosmos harbors jets that don't glow at all? Picture a dark star, silent and invisible, suddenly convulsing as it hurls a torrent of dark matter particles into space at nearly the speed of light. This isn't just an eruption, it's a phantom jet, a cosmic ghost train ripping through the fabric of reality, leaving no visible trace, only destruction in its wake. The mechanics defy ordinary physics. In a typical star, jets form when magnetic fields channel charged particles into narrow beams, but a dark star's jet would be sculpted by forces we can barely measure. Imagine dark matter particles, whatever they are, colliding and annihilating in the star's core, their energy funneled by twisted magnetic fields woven from exotic, unseen currents. The result, a beam so dense with invisible particles that its gravity alone would warp the path of anything nearby. Galaxies drifting too close might find their outer stars tugged sideways, their gas clouds stretched into bizarre, filamentary shapes. Entire star clusters could be sent careening off course like leaves caught in the wake of a passing truck. Astronomers might have already witnessed the aftermath without realizing it. Across the universe, some galaxies exhibit bizarre, high-velocity winds, rivers of gas streaming outward at thousands of miles per second, far faster than supernova or black hole activity can explain. The culprit could be a dark star's phantom jet, plowing through interstellar material like an invisible plow. Without light to mark its path, the jet's presence would only be betrayed by the chaos it leaves behind. Gas clouds ionized by unseen turbulence, star-forming regions ripped apart by gravitational shearing, even entire galactic arms bent into unnatural arcs. The smoking gun might lie in the details of these distortions. Ordinary astrophysical jets, like those from quasars, heat surrounding gas to extreme temperatures, producing X-rays and radio waves. A phantom jet's footprint would be colder, quieter, its effects purely gravitational. Picture a galaxy where one side seems compressed, its stars and gas pressed into a dense, unnatural wall, while the opposite side flares outward as if shoved by an unseen force. Telescopes mapping galactic winds have spotted these lopsided patterns, their origins still debated. But if the models are right, they could be the cosmic equivalent of tire tracks, evidence of something massive and invisible passing through. The hunt for phantom jets is pushing astronomers to rethink how they observe the universe. Traditional telescopes are useless here. Instead, researchers rely on gravitational lensing surveys, searching for subtle warps in the shapes of distant galaxies that might reveal the jet's path. Others track the motion of hypervelocity stars, lonely suns racing through space at impossible speeds, looking for clusters that seem to originate from nowhere, as if ejected by an invisible slingshot. The most tantalizing clues might come from the cosmic microwave background, where phantom jets could imprint faint, linear scars, stretches of sky where the afterglow of the Big Bang is slightly colder, its light subtly bent by the jet's passage billions of years ago. What's at stake isn't just another exotic cosmic phenomenon. If phantom jets exist, they'd prove that dark matter isn't just a passive ingredient in the universe's recipe. It can erupt, flow, and sculpt the cosmos as dramatically as any force we can see. They'd challenge our assumptions about how galaxies evolve, offering an explanation for the mysterious winds and distortions that have puzzled astronomers for decades. And most tantalizingly, they'd hint at an entire hidden layer of astrophysics playing out in the darkness where the universe's most powerful engines don't shine, they pull. Every unexplained warp, every rogue star, every galaxy bent out of shape could be a message from the dark waiting to be read. Imagine a crown of shadows stretching across the cosmos, not carved from light, but woven from particles that barely acknowledge the universe's rules. This is the dark star's halo, a vast, whispering cloak of weakly interacting matter enveloping its unseen host. Unlike the blazing coronas of ordinary stars, this halo doesn't glow or flicker. It doesn't even reflect. Instead, it absorbs a cosmic sieve, straining the faintest whispers of radiation from the void around it, leaving behind a ghostly imprint on the oldest light in existence, the cosmic microwave background. The halo's construction defies intuition. Picture trillions of exotic particles, actions, neutralinos, or other dark matter candidates trapped in a slow, gravitational dance around the dark star. These particles don't collide like atoms in a gas. They pass through one another like ghosts through walls, their interactions so feeble they're practically untouchable. Yet collectively, their mass is enough to bend space-time, creating a lens so subtle it distorts the universe's afterglow in ways barely detectable. To an observer, the effect would resemble a smudge on a window pane, a patch of the cosmic microwave background ever so slightly cooler than its surroundings, as if something had briefly blotted out the fire of creation itself. The hunt for these halos is rewriting how we map the invisible universe. Telescopes like the Planck satellite have already catalogued anomalies in the microwave background regions where the temperature dips inexplicably. Most are dismissed as statistical noise or the echoes of ancient cosmic voids, but a handful align too perfectly with gravitational lensing maps, their positions overlapping with patches of space where something massive seems to lurk. Could these be the fingerprints of dark stars and their halos, their combined gravity warping the universe's oldest light like fingers pressing into clay? The implications stretch far beyond mere detection. If halos exist, their structure could reveal dark matter's true nature. Some models predict these halos should be smooth, their particles distributed evenly like fog. Others suggest they'd clump into filaments or subhalos, swirling around the dark star like satellites around a planet. Observing even one halo's texture, whether through its lensing signature or its effect on passing cosmic rays, could settle decades of debate about dark matter's behavior on scales we've never probed. But the most tantalizing possibility lies in the halo's longevity. Unlike ordinary stars whose outer layers evaporate into stellar winds, a dark star's halo might persist for trillions of years, outliving galaxies themselves. These halos could be the universe's final monuments, silent, shadowy witnesses to the end of all light, their presence etched into the cooling embers of space-time long after the last sun has burned out. For now, they remain phantoms in the data, their existence hovering between theory and revelation. Yet with every anomalous cold spot in the cosmic microwave background, every unexplained warp in distant starlight, we edge closer to a truth that would reshape our understanding of the cosmos. That darkness isn't just the absence of light. It's a presence, a structure, a thing with weight and shape casting shadows we're only beginning to see. At the farthest edge of theoretical physics, where imagination collides with the equations scribbled on blackboards, lies a possibility so radical it redefines the word star entirely. Picture a dark star not just as an object, but as a rip in reality itself, a cosmic whirlpool where space-time doesn't merely bend, but folds, creating a bridge to somewhere or someone else. This isn't science fiction. It's a fringe but mathematically plausible vision of a dark star as a multiverse portal, a natural wormhole forged from the very fabric of dark matter. The idea hinges on a peculiar twist of Einstein's general relativity. Normally, matter warps space-time like a weight on a trampoline, but under extreme conditions, like those inside a collapsing dark star, the fabric of reality might twist so violently that it pinches off, forming a tunnel between two distant points. Traditional wormholes are theorized to require exotic matter with negative energy to stay open, a substance we've never observed, but a dark star's core, pulsing with the annihilation of dark matter, could offer something even stranger, a self-sustaining vortex where the peculiar physics of dark particles provide the stability exotic matter can't. Imagine the mechanics. As dark matter annihilates in the star's heart, it doesn't just release energy, it warps the quantum fields around it, creating a feedback loop where space-time buckles inward like a Möbius strip. The result, a tunnel threaded through higher dimensions, invisible to light but palpable to gravity. Matter or radiation falling toward the dark star wouldn't just vanish into darkness. It might emerge somewhere entirely different, another universe, another time, or a parallel reality where the laws of physics themselves are subtly skewed. The evidence might already be hiding in plain sight. Some active galactic nuclei, the superbright cores of distant galaxies, exhibit bizarre energy signatures that defy black hole models. Jets of particles shoot out not just from their poles, but at odd angles, as if space itself is leaking. Could these be the echoes of a dark star's tunnel, its gravitational grip funneling matter not into a singularity, but into another branch of the multiverse? Even stranger, certain high-energy cosmic rays arrive with particles that seem too young to have traveled the distances they've crossed. Did they take a shortcut through a space-time defect we've yet to map? The implications spiral beyond astronomy into philosophy. If dark stars can stitch realities together, they'd be less like objects and more like events, cosmic stitches in the quilt of existence. A civilization advanced enough to map them might not even need spaceships to explore the cosmos. They could simply step through, but there's a catch. Crossing a natural wormhole would be a one-way trip. The tidal forces near its throat would shred any known material, and the laws of causality might unravel entirely. You wouldn't travel so much as unbecome, your atoms scattered across dimensions like ink in water. Yet the math refuses to dismiss the idea. String theory allows for brain-worlds, parallel universes floating like sheets in higher dimensional space, and dark stars could be the bruises where these sheets touch. Quantum foam, the froth of virtual particles at the smallest scales, might churn into stability around a dark star's core, weaving a tunnel where probability itself takes on new shapes. It's a dizzying thought that the universe's darkest objects might also be its brightest doors, waiting for a knock from someone or something on the other side. For now, these portals remain phantoms in the equations, but with telescopes now capable of sensing the faintest gravitational ripples and particle detectors probing the edges of quantum reality, we might soon stumble upon a signature too strange to ignore. A burst of particles with no origin, a galaxy spinning the wrong way, or perhaps just a whisper in the data, hinting that the cosmos isn't just vast, it's connected, in ways we're only beginning to dream. Deep in the void where silence should reign supreme, an invisible orchestra might be tuning its instruments, not with sound but with gravity itself, ripples in space-time pulsing outward like the slow, resonant notes of some cosmic bassoon. This is the Dark Stars Symphony, a composition played not for ears but for the fabric of reality. Every object in the universe vibrates, planets hum. Stars ring like bells after stellar quakes, even black holes chirp when they collide. But a dark star's music would be different, darker, heavier. its frequencies shaped by the peculiar physics of its invisible core. Picture this: deep within the star, dark matter particles collide and annihilate, their interactions sending shock waves through the star's structure. These waves don't travel through gas or plasma like ordinary sound. Instead, they warp spacetime itself, vibrating the star's gravitational field like a drumhead struck by an unseen hand. The result, a low, throbbing hum resonating across light years, detectable only by the most sensitive gravitational wave observatories. The melody would be unlike anything we've recorded. Traditional gravitational waves from black hole mergers are brief crescendos, sharp, crashing chords that fade in seconds. A dark star's vibrations, though, could last for centuries, their tones shifting as the star's internal dynamics evolve. Some frequencies might correspond to the star's rotation, a deep, droning bass note as it spins. Others could arise from asymmetries in its core, like a cracked bell producing dissonant overtones. If we could tune into this symphony, it wouldn't just reveal the star's mass and size, it would expose the hidden structure of dark matter itself. Future detectors could turn this theory into revelation. Existing observatories like LIGO are built to catch the universe's loudest crashes, but next-generation tools will listen for whispers. The Laser Interferometer Space Antenna, or LISA, scheduled to launch in the 2030s, will float in orbit free from Earth's seismic noise, its arms spanning millions of miles. This colossal ear will be tuned to lower frequencies, perfect for catching the dark star's basso profundo. Even more ambitious proposals, like the Cosmic Explorer ground-based detector, could pick up harmonics in the star's vibrations, revealing whether its core is smooth or fragmented, whether it pulses like a heart or quivers like a struck gong. The real breakthrough would come from comparing notes literally. Just as seismologists use earthquakes to map Earth's interior, astronomers could analyze a dark star's gravitational vibrations to reconstruct its hidden architecture. A star with a dense, compact core might produce sharper, higher-frequency waves. One with a diffuse halo of dark matter could generate a broader, resonant boom. And if the vibrations drift over time, slowing as the star consumes its dark fuel, or shuddering abruptly as internal pressures shift, it would be like hearing the star's life story in real time, a cosmic biography written in spacetime tremors. Yet the grandest implication isn't just hearing the music, it's decoding it. Dark matter's particles have eluded every lab experiment designed to catch them. But a dark star's gravitational waves could carry fingerprints of those particles' properties, their mass, their interaction strength, even hints of their quantum behavior. A tremor that dampens too quickly might suggest friction between dark matter components. A tone that lingers could mean the particles barely interact at all. Each fluctuation, each harmonic, would be a clue in a puzzle spanning the entire cosmos. For now, the symphony remains theoretical, its score written in equations rather than data. But as our detectors grow more sensitive, as we learn to listen not just for crashes but for whispers, the void might yet yield its secrets. And if we're patient, if we attune ourselves to the universe's deepest rhythms, we might finally hear the dark stars singing. Even in total darkness, quantum physics ensures nothing stays completely black. Far from the light of ordinary stars, a dark star might emit a whisper of radiation, not from nuclear fires, but from the bizarre quantum effects at its edge. This is Hawking radiation, the faint thermal glow predicted to escape from objects so massive they warp the fabric of reality. For a black hole, this glow is trillions of times weaker than starlight. But a dark star, its unique structure could turn this quantum whisper into something almost detectable. Picture the surface of a dark star. Unlike a black hole's event horizon, where space plunges inward forever, a dark star's boundary might be a place of quantum turmoil. Virtual particles flicker in and out of existence at the edge of its gravitational grip. Normally, these particles annihilate instantly, but under the star's extreme gravity, some could be torn apart. one particle swallowed by the star, the other cast into space as radiation. Multiply this effect over the star's entire surface, and you'd get a feeble but constant glow, a thermal signature with a temperature just above absolute zero. Here's the catch: this glow isn't just dim, it's frigid. A supermassive dark star could emit Hawking radiation at temperatures measured in billionths of a Kelvin, far colder than the cosmic microwave background. To detect it, we wouldn't just need sensitivity, we'd need proximity. Imagine parking a telescope so close to the star that its sensors practically brush against the dark star's surface. At a distance of 1 astronomical unit, the span between Earth and the Sun, the radiation would still be drowned out by the universe's ambient noise. But shrink that gap to the width of our solar system's inner planets, and the signal might finally rise above the cosmic static. The numbers are daunting. A dark star with the mass of 1,000 suns would emit roughly a picowatt of Hawking radiation, a trillionth the power of a smartphone's laser pointer. Catching that signal would require instruments chilled to near absolute zero, shielded from every stray photon, and positioned closer to the star than Mercury orbits our Sun. Even then, the star's own gravitational distortions would warp spacetime so severely that light from background stars would bend unpredictably, creating optical noise that could mask the Hawking glow. Yet the payoff would rewrite physics. Detecting this quantum whisper wouldn't just confirm dark stars exist, it would prove that Hawking radiation is real, offering the first direct evidence of quantum gravity in action. It could reveal whether dark matter particles decay into detectable byproducts when annihilated near the star's surface. And if the radiation spectrum deviates from predictions, it might hint at new physics beyond the standard model, clues buried in the coldest light in the universe. For now, the hunt remains a clash between theory and engineering. Telescopes like the James Webb Space Telescope can't see such frigid wavelengths, and no probe has ever ventured close enough to a candidate object to test the hypothesis. But as sensors grow more sensitive and dark matter models sharpen, we might one day tune our instruments to the universe's quietest song, a thermal hum from the edge of nothingness waiting to be heard. The cosmic web stretches across the universe like an invisible skeleton, its dark matter filaments weaving galaxies together in a vast, interconnected tapestry. Now picture something far stranger anchoring those threads: a dark star, not merely drifting in the void but serving as a gravitational keystone, a silent architect holding entire swaths of the universe in place. These stars wouldn't just exist within the cosmic web. They could be the invisible pillars that shape it, their immense mass sculpting the flow of dark matter over billions of years. Think of the cosmic web as a spider's silk, delicate but unimaginably strong, with galaxies clustered like dewdrops along its strands. Without dark matter's gravitational glue, this structure would collapse. But dark stars add something new to the equation. Unlike diffuse dark matter halos which spread their influence smoothly, a dark star's concentrated gravity could act like a knot in the web, a focal point where filaments intersect and tighten. Simulations of large-scale structure formation show dense nodes where dark matter flows converge. Some of those nodes flicker with anomalies, pockets of gravity stronger than ordinary models predict. Could these be the fingerprints of dark stars, their invisible bulk warping the web's design? The evidence might lie in the motion of galaxies themselves. Astronomers map the cosmic web by tracing how galaxies move, their paths betraying the pull of unseen mass. Yet some galactic streams flow in peculiar ways, as if tugged by something dense and hidden. Take the case of the Pisces-Perseus supercluster, a river of galaxies spanning over 1 billion light-years. Along its length, certain galaxies accelerate unexpectedly, their trajectories bending toward regions with no visible mass. Traditional models attribute this to diffuse dark matter, but a network of dark stars scattered along the filament could explain the sharper, more localized deflections, like invisible buoys redirecting a current. Then there's the question of timing. The cosmic web didn't form overnight. In the early universe, dark matter clumped into faint tendrils and ordinary matter followed, pooling into galaxies. But some filaments seem too well defined, their galaxies too neatly aligned, as if something had pinned them in place during the universe's chaotic adolescence. Dark stars, born from the densest dark matter peaks in the primordial cosmos, could have provided those anchors. Imagine a seedling's roots gripping loose soil. Without them, the plant topples. Without dark stars, perhaps some filaments would have frayed, their galaxies scattering into the void. The hunt for these nodes is pushing astronomers to rethink their tools. Traditional surveys map the web by observing galaxies, but dark stars demand a subtler approach. Gravitational lensing studies now scan the empty spaces between galaxies, searching for phantom distortions, tiny, unexplained warps in background light that suggest concentrated mass where none should be. Other teams analyze the cosmic microwave background for cold spots aligned with filament intersections, residues of dark stars chilling the universe's oldest light as they gathered matter eons ago. Yet the grandest implication isn't just finding dark stars, it's understanding how they shape the universe's evolution. If these invisible anchors exist, they'd rewrite the story of how galaxies form, suggesting that dark matter's influence isn't just broad and diffuse, but punctuated by dense, invisible lighthouses guiding cosmic growth. They'd hint that the universe's largest structures aren't just woven from dark matter's threads, but stitched together by something even more enigmatic: dark stars, the hidden needles in the cosmic loom. A planet orbiting a dark star wouldn't need sunlight to be warm, just the silent, ceaseless churn of dark matter annihilation in its core. Picture a world suspended in eternal night, its surface heated not by a glowing star but by the invisible particles colliding in the darkness above. This is the dark star's habitable zone, a region where the energy released by dark matter interactions could maintain liquid water, thick atmospheres, and perhaps even the delicate chemistry of life, all beneath a sky devoid of any sun. The mechanics are unlike anything in our solar system. Around ordinary stars, habitable zones are calculated based on radiant heat, the Goldilocks distance where water neither freezes nor boils. But a dark star's warmth would come from within. As dark matter particles in the star's core annihilate, they'd release energy that seeps outward, heating any nearby planet through conduction and convection rather than light. The surface temperature wouldn't depend on sunlight at all, but on the planet's depth in the star's gravitational well and the density of dark matter flowing through it. A world orbiting too close might be scorched by this invisible furnace. Too far, and it would freeze in the interstellar void. Yet somewhere in between, there could be a sweet spot where heat and chemistry align perfectly. Imagine the landscape of such a planet: no sunrise, no sunset, just an unbroken black sky, its emptiness occasionally punctuated by the faint infrared glow of atmospheric gases stirred by geothermal vents. With no light for photosynthesis, life would rely on chemosynthesis microbes feeding on the chemical energy of subsurface reactions, much like the extremophiles huddled around Earth's deep-sea hydrothermal vents. But in this perpetual twilight, evolution might take stranger turns. Predators could develop exquisite sensitivity to vibrations in their dense, humid air. Plants, if they exist at all, might grow in sprawling, heat-seeking mats, their structures optimized to absorb thermal radiation rather than light. The real puzzle is time. On Earth, the rhythm of day and night drives biological cycles from sleep to migration, but on a dark star's planet, timekeeping would demand alternatives. Tidal forces from the star's gravity could stretch and compress the world in regular intervals, creating subterranean tides that organisms learn to anticipate. Or life might sink to the faint pulses of the dark star itself, its core's annihilation rate fluctuating over millennia like a slow, cosmic heartbeat. Some theorists even suggest such ecosystems could evolve in layers surface dwellers adapted to the faint trickle of heat from above, while deeper creatures thrive near volcanic plumes, their biology tuned to completely different energy gradients. Yet the most haunting question isn't whether life could exist here, it's whether it could ever leave. Without sunlight, photosynthesis is impossible, meaning no oxygen-rich atmosphere to fuel fire or technology. Civilizations, if they arise, might develop entirely in the planet's crust, their energy drawn from geothermal or nuclear sources, their skies forever unknown. They could orbit their dark star for billions of years, utterly unaware of the universe beyond, their entire cosmos bounded by the reach of their star's faint warmth. Astrobiologists call these rogue planets, the universe's greatest survivors, worlds adrift in the void, their only heat coming from radioactive decay or tectonic friction. But a dark star's planet would be something stranger, a world not wandering but bound eternally to an invisible master, cradled in a warmth that leaves no trace in the sky. If life thrives there, it would be proof that biology doesn't need light, just energy, patience, and the unfathomable creativity of evolution in the dark. For now, these worlds remain speculative, their conditions so alien that even our most advanced telescopes wouldn't recognize them. But as we refine our models of dark matter and study the extremophiles thriving in Earth's own lightless corners, the idea grows less outlandish. The universe has already shown us life's tenacity in impossible places. Why not on a planet where the only star is one we cannot see? At the farthest edge of theoretical astrophysics, where mathematics blurs into speculation, there could lurk a dark star so unfathomable it doesn't just bend the rules of physics, it rewrites them entirely. This is the ultimate dark star, a celestial anomaly so dense, so impossibly massive, that its very existence teeters on the brink of cosmic catastrophe. Imagine a gravitational titan formed not from mere dark matter, but from the primordial seeds of reality itself, a relic from the universe's first microseconds when the forces of nature were still fused into a single, seething unity. Unlike any other object in our cosmic inventory, this dark star wouldn't just collapse into a black hole. It might collapse the fabric of space-time around it, inching toward a critical threshold where gravity triumphs over all other forces, triggering a chain reaction that could unravel existence itself. The danger lies in its birth. Most dark stars form from the slow accumulation of dark matter, but this one could be different, a runaway product of the Big Bang's most violent instance. Picture the early universe, a fraction of a second old, when quantum fluctuations in the newborn cosmic soup occasionally spat out pockets of absurdly dense energy. Most of these anomalies smoothed out as the cosmos expanded, but what if one survived, a knot of dark matter so concentrated that it carried the weight of a galaxy in a volume no larger than a proton? Over billions of years, this speck would gorge on surrounding dark matter, growing in silence until its core reached a density where the equations of general relativity start to scream in protest. At this scale, the star's gravity wouldn't just warp space-time, it would destabilize it. Quantum mechanics forbids singularities from forming outside black holes, but the ultimate dark star would flirt with disaster, its core compressing until the very concept of inside and outside breaks down. The vacuum of space around it might begin to decay, bubbles of alternative physics blossoming like cracks in ice. Some theories suggest such an object could act as a seed for vacuum metastability, a phenomenon where a single point of extreme gravity triggers a phase transition in the universe, rewriting the fundamental constants of nature in an expanding wave. One moment, the laws of physics as we know them; the next, a new reality where atoms can't form, light can't travel, and existence as we understand it ceases to function. The strangest part, we might never see it coming. A dark star this extreme would cloak its threat behind absolute invisibility. No light, no Hawking radiation, not even the faintest thermal whisper. Its presence would only be betrayed by its gravitational vandalism, galaxies torn apart by unseen tides, cosmic voids where the microwave background flickers with inexplicable coldness, or perhaps a faint tremor in the gravitational wave background, a slow drumbeat counting down to an unfathomable event. Astronomers could spend centuries mapping these anomalies without ever piecing together their source, like detectives tracing the footsteps of a ghost. Yet the ultimate dark star's true horror isn't its power, but its patience. It wouldn't explode or evaporate. It would simply persist, hovering at the edge of impossibility, its gravity inching closer to the critical threshold with each passing eon. Given enough time, trillions of years, perhaps it might cross that line. And then, in a silence deeper than the void, it would rewrite the universe's final chapter with a single, unstoppable thought: let there be nothing. For now, these monsters remain mathematical phantoms, their existence balanced on the razor's edge of hypothetical physics. But their shadow lingers in the data, in the unanswered questions at the frontier of cosmology. Why does dark matter clump so unevenly? Why do some gravitational lenses defy all predictions? And most haunting of all, have we already glimpsed the edges of something vast, unknowable, and waiting in the dark? We've journeyed through 25 of the cosmos' most chilling enigmas, dark stars that defy every expectation, from primordial giants woven from dark matter's first whispers to rogue wanderers drifting unseen between galaxies. Each one is a key to unlocking the universe's deepest secrets. Imagine proving that supermassive black holes were never black holes at all, but dark stars in disguise. Or discovering that phantom quasars, those brilliant cosmic lighthouses, are actually shadows cast by something far stranger. The implications would ripple through astrophysics like a shockwave, forcing us to rewrite textbooks, rethink gravity, and perhaps even redefine what a star can be. Consider the gravitational lensing anomalies we can't explain, the rogue planets heated by invisible fires, the strange, rhythmic pulses in gravitational wave data that sound like a heartbeat from the void. Every unanswered question in modern astronomy, from the universe's missing mass to the bizarre behavior of ancient quasars, might find its answer in these shadowy titans. Dark stars aren't just celestial oddities, they're a mirror held up to the limits of our understanding, reflecting all we've yet to learn. So as we close this exploration, let's not just marvel at the possibilities, let's question them. What if the first dark star discovery is already hiding in plain sight, buried in old telescope data? What if the universe is teeming with these invisible giants, their gravity sculpting everything from galaxy clusters to the cosmic web itself? The hunt is far from over. With every new observatory, every breakthrough in dark matter research, we edge closer to peeling back the veil. Now it's your turn. Which of these dark stars fascinates you most? Could there be even stranger variants lurking beyond our theories? Drop your thoughts below. The universe's greatest mysteries are waiting, not just for scientists, but for anyone daring enough to look into the dark and wonder.